Okay, as we start our discussion of gases in this unit, a new measurement device that we'll need to discuss that we haven't talked about before is pressure. Now, pressure, the equation for pressure is force over area, and you can refer to pressure to a lot of different scenarios, but of course in gases we're going to talk about the pressure caused by gas molecules. Now, we already know that gas molecules have a lot of degrees of freedom, and they take up the entire space of the container, the entire volume of the container. They rarely interact with each other, and they've got a lot of kinetic energy to sort of bounce around. And when they do so, they when they strike the interior of the container that they're being held in, that it creates a force on that area, and that is something we can define and measure as pressure. One of the ramifications of this, because gases take up the entire volume of the container, we're going to have to discuss density a little bit differently. We can add more molecules to, say, this container of gas molecules. This would be at lower pressure. The more molecules we add, it increases the pressure. But it also sort of changes what we've talked about density. Density we've always referred to as mass divided by volume, because we can add more gas molecules to the same volume container. We're going to have to sort of rearrange our terminology for density for gases, and it turns out that that's quite easy to do and easy to calculate and determine. So how do we measure pressure? So how do we measure pressure? One of the first instruments utilizing trying to measure pressure was a Mercury barometer. Okay, so it turns out that all around us we have, of course, the atmospheric gas molecules, nitrogen, oxygen, so on. They, of course, create a pressure on us that we feel every day. And one way to measure that pressure was to incorporate an evacuated glass tube, meaning a small glass capillary where they sucked all the air out, and they submerged it in a mercury reservoir of mercury liquid. What happens is that all of the gases in the atmosphere exert a pressure on this mercury reservoir and actually push mercury up the evacuated glass tube. And they would actually measure the height at which mercury rose in that glass tube, or in that barometer. So our initial measurement terms for pressure were actually distances, height of mercury that rose up a barometer. And so if you measured the atmospheric pressure at sea level, you'd get 760 millimeters of mercury, meaning that mercury rose 760 millimeters up the barometer. So this is our sea level pressure. Okay. We also, since then, more contemporary terminology for millimeters of mercury is the torr. So this can also be written as 760 torr, T-O-R-R. Okay, because this is the pressure at sea level, or the atmospheric pressure. We also came up with another unit of measurement, the atmosphere. So 1 atmosphere, or ATM, equals 760 torr. So torr and atmospheres are primarily the units of pressure that we will utilize in a chemistry course. But of course there are several other units of pressure that you've probably experienced in everyday life, or will come across maybe in a different course or different setting. There are, of course, pascals, which is, if you think about the equation for pressure, force over area, force unit is newtons, area, meters squared. And what that gives you is the Pascal. And these are all the equivalents for atmospheric pressure. So these all equal 1 atmosphere. So we can, of course, use these as conversion factors if we need to. And so other pressure terms, pounds per square inch, PSIs that you've heard before. And of course, you know, if you fill up your automobile or bicycle tires, you fill them up to some prescribed pounds per square inch PSI level, and it turns out that the in 1 atmosphere is 14.7 PSIs. 760 torrs, as we previously said. You can also measure the height that Mercury traveled up the barometer in inches, and that's the inches of Mercury units, 29.92 at sea level, and of course atmospheres. Okay, so now we're going to talk about some of the relationships between units of measurement for gases. And these can be described as the simple gas laws, and the first one is Boyles' law, and this, of course, is the relationship. Boyles' law describes the relationship between volume and pressure. Okay, and you can probably come up with this relationship just thinking about experiences. If you have a balloon, it has some volume. What would happen if you increase the pressure on the outside of that balloon? Okay, or squeeze it? Of course, the volume would decrease. So it turns out that volume and pressure are inversely proportional, meaning that as pressure increases, the volume will decrease. And you get a plot, something like that. Okay, and we can write that mathematically, or as a mathematical expression, is volume is inversely proportional to P. Okay, from this function, from this plot, we can get a slope, M. We can turn this into a proportionality constant. Which we can describe as K. And it turns out that if you measure the volume and pressure at any one point and look at the product of them, you will get that proportionality constant K. You can do this experiment at, say, 2 different points in your graph. And therefore you would get 2 different values. Let's say volume initial and the initial pressure, V1, P1. V2, your second experiments, V2, P2, will also equal that proportionality constant. Now, since those expressions are equal to the same constant, we can say V1, P1 equals V2, P2. So you can derive an equation for Boyles' law to indicate that if you know the initial volume and pressure settings, and you change one to, say, increase the pressure, you can calculate V2, the secondary pressure, by solving for it. Here's an illustration of Boyles' law from a molecular point of view. So if you have a piston and gas molecules in there in 1 liter at a pressure of 1 atmosphere, if you double the pressure to 2 atmospheres, of course you are going to exert a force on that piston, in this case, and decrease the volume by half to 0.5 liters. The next law we're going to discuss is Charles' law. And this describes the relationship between volume and temperature. Okay? So again, you could probably describe this relationship from your previous knowledge as well. If you increase the temperature of something, we know that it expands, and that's always and dramatically the case for gases. Temperature and volume are directly proportional, meaning that if you increase the temperature, you're going to increase the volume. Now, just as we did with Boyles' law, we can get a slope of this function, of this line. We can turn that into a proportionality constant. And because they're directly proportional, now the division of volume over temperature will give us that constant, V1, V over T. We can do that experiment again in 2 different settings, V1, T1, and V2 over T2. And that will give us the same constant. And so, of course, since these are both equal to the same thing, we can set them equal to themselves. V1, T1 equals V2, T2. So just like Boyles' law, we've got a mathematical relationship for Charles' law. And so if you know initial volume and temperature, and say you decrease the volume, you can predict what temperature caused that. Here's an illustration of Charles' law. And if we throw a balloon in ice water, of course the temperature, the temperature of the ice water, if it's lower than the air in the balloon, the heat will transfer from the air molecules in the balloon to the water, lowering their kinetic energy, decreasing the force in which they impinge on the interior of the balloon, causing the volume to decrease. If we threw that same balloon in hotter water, boiling water, we'd give those air molecules more kinetic energy, increasing the force that they strike the interior of the balloon, of course increasing the volume. Okay, the third law we can discuss is Avogadro's law. Now we remember Avogadro's number. That had to deal with the number of atoms in a mole. So it's not surprising that Avogadro's law describes the relationship between number of moles, N, as we're going to call it now, and volume. Now this is probably the easiest to come up with. If you blow more air molecules in a balloon, what happens to the volume? Well, of course it increases. So the number of moles and volume are also directly proportional. Just like as we did in the two previous laws, we can develop a proportionality constant from the slope. So we can create a scenario where we have N1 over V1 equals N2 over V2, or vice versa. And so we've got a mathematical relationship according to Avogadro's law. Okay, it turns out that if you combine all of those proportionality constants into the three separate laws, Boyles, Charles, and Avogadro's law, you can walk away with an overall reaction that gives you an ideal gas constant instead of the individual proportionality constants, and that is what we call R. Now, depending on your R's, you can have different units for R. Primarily, we're going to use units of liters, atmospheres, moles, and Kelvin. So we have 0.08206 if we use liters, atmospheres, and moles, and kelvins. And actually, I didn't really say this previously, but for temperature, we should always use Kelvin as our units for temperature because it's an absolute measure of temperature, not a relative one like degrees Celsius or Fahrenheit. A doubling in temperature of Celsius is not necessarily a doubling of absolute temperature. Although because Kelvin is an absolute measure, a doubling in temperature of Kelvin is a double in temperature. Okay, and when you combine all three gas laws, volume inversely proportional to pressure, so V1 P1, V over T, V over N for those relationships, you combine those to the ideal gas law, V equals nRT over P, and this is primarily written as PV equals nRT. So now we've got an equation that says if you know the pressure, volume, and temperature, you can calculate the number of moles. If you know the number of moles, temperature, and pressure, you can calculate volume. If you know any of the three variables,